Okay, so hello everybody. Welcome to the One World Mind Seminar on October 9th, 2025. I'm here today introducing the illustrious, the awesome Dr. Anna Veselovska, who is going to talk to us today about gradient descent and implicit bias in tensor factorizations. And I think you will find it amazing. All right, I'll turn things over to you. And I apologize for the introduction.
Thank you, Mark. Thank you for inviting me to give a talk, and thank you for the kind introduction. As Mark already mentioned, I would like to talk today about gradient descent and implicit bias in tensor factorizations. And what I want to mention is that this talk is based on the work that I did with Santosh Karnik, Felix Kramer, and also with Mark. And the underlying work of this is our recent publication. I will start with some motivation then. So the motivation for us is the mystery of gradient descent in the learning theory. And for example, we are interested in the following phenomenon: why small random initialization and gradient descent effectively find well-generalized global optima, despite that we have non-convex problems and we have over-parameterization. And so what recent results show that in over-parameterized regimes, gradient descent implicitly regularizes towards simple structures. And there are different notions of simple structures. For example, the one that are very well understood is are simplest structures in matrix settings. So we have the following implicit bias of gradient towards sparse solutions when we have Hadamard factorization. And there are a lot of works in this direction. And for example, in the case when we have matrix factorization, then we have implicit bias towards low-rank solutions. And there are also a line of works in this direction. So implicit bias in matrix setting is very well understood from the theoretical point of view. And our goal is to understand implicit regularization of gradient descent in tensor setting. For this talk, we will focus on tubal tensor factorization. This type of factorization is also motivated by video processing. And why we talk about factorization in general. So tensor factorizations, they are very useful when we try to understand or I would say work with neural networks. For example, there are some works that show that tensor factorizations correspond to a specific shallow nonlinear convolutional networks, and also some dense weight matrices of a full connected layer of a neural network can be converted to a tensor train. And the advantage in this case is that this tensor train will preserve the expressivity of the corresponding layer. Also in signal processing, there are many applications of, in this case, specifically tubal tensors. And they are highly used in video processing. Then why we also want to focus on low rank factorizations. Like as I mentioned before, there are particular structures that are considered as simple. For us, the simple structure for tubal tensors will be low tubal rank tensor. And we want to extend the matrix paradigm to the tensor case. And in the matrix paradigm, what we know is that gradient descent applied to matrix factorization recovers low rank representations from linear observations. And when we go to the tensor setting, the main challenge is then that there is no unique notion of a tensor rank or a tensor factorization. And what we can learn from the literature is the following, that certain types of factorization need certain time of low rankness. So which means if we have a certain time of factorization, then it needs to correspond to a certain type of low rank that is to be recovered. So far, there is no, I would say, research that are available for implicit regularization with small initialization for low tubal rank. They are only available, or for low tensor rank in general. They are only available for gradient flow. For example, the work from 2021, they look at the CP rank factorization. So this is another type of tensor factorization, and CP rank, and show that the gradient descent has there also some implicit regularization or gradient flow. And there are also some specific types of hierarchical tensor factorizations that also have been considered recently, but they are also for gradient flow. So in a small initialization setting, no results on implicit regularization towards low tensor rank are available. And that's why we were motivated to look at this case and to see what we can do. But before we go to our result, I want to introduce the notion of tensor, tubal tensor product. What are these tubal tensors, how they work, and what we need to look at. And here is a very simple intuition how tubal tensor product works. We start with something that we know very well. So we know matrix product. We know that if we want to multiply two matrices, V and W, right? Then to get an ij element of this product matrix, what we need to do, we need to take the row and multiply this with j's column. And in such way, we will get the x that is the product of w and v. And every xj has here a sum of real numbers. So we multiply two vectors and we get a real number out of it. If we go to tensor, tubal tensor product, then it works. It has a very similar intuition, but we add here an extra dimension. And tubal tensors, you can think about them in general as having a matrix of tubes. And these tubes, they are of this extra dimension, of dimension k. And what you want to have similar idea as for matrices. To compute the I and j element of this tensor, you want to multiply I row of tubes with j row of tubes, and you want to get a tube out of it. And this is something that you can do. So you can say, I have here, in the matrix case, I have a product of real numbers, and it gives me a real number. And in the tensor, tubal tensor setting, you have product of vectors, and you want to have a vector as a result of this. So we'll have a sum of vectors. And this can be done, for example, if you do here the convolution. You convolve two vectors, and they will give you a vector of the same dimension. So this is the intuition behind tubal tensor product, right? So there is this, I would say, idea has been borrowed from matrix setting. And for such type of products, there is a strict tensor factorization. So if you can, as you can see here in the picture, we have a tensor x in blue, and it has its tubal SVD. So the tubal SVD has the following form as depicted here. So we have two matrices V and W that are orthogonal, and we have in the middle a frontal slice diagonal tensor. And this frontal slice diagonal tensor, it means that if you consider the frontal slices of it, then you will get a diagonal matrix. And I think that here should be W and V. So I now noticed a typo, but you understand what I mean. Look at this picture. This is what is very important. So here you also can see that it has some similarity with the matrix case, but it has also some additional notions. And for example, the tubal rank of a tensor then is the number of non-zero tubes in sigma. So sigma is this frontal slice diagonal tensor. And then in this case, for this picture, then the rank would be, is 6, right? And because we have here 6 non-zero tubes. So in this case, we can say that this is a full rank tubal tensor. And for facet, I will use the following notation. So all these singular tubes that are in sigma, I will denote by sigma, small sigma I, but they are all vectors. So do not mix them with singular values in the matrix case, because in my slide, sigmas will be mostly vectors when we talk about X. There will be also some case where it is not a vector but a number, but I will tell you when it is. And in this picture, for example, you can see an example of a low-rank tensor. So as you can see, I have here some white tubes in this middle tensor, which means, for me, it means that they are 0. And the blue one, they are not 0. Of course, this one that are in V and W, they are also marked like white, but they are just inactive. So you have here just the blue part of this SVD decomposition that is active. You can think about this as the reduced form of the SVD, right? And for such tensors, there is also the concept of tensor column subspace. For example, for this tensor X that has rank R, this tensor column subspace will be spanned by the first R lateral slices. So you can see them here, the first 4 and blue lateral slices of the tensor V. Okay. Then also what is very important for tensors in the tubal tensor setting is the so-called tubal tensor. There's the tubal tensor domain and the Fourier tensor domain. So if we see here, this is the same setting as we had before. We have a tubal tensor of this dimension. We have tubes. So the tubes, they are vectors that go in the k direction, in this extra direction, in the third direction. And we know that we multiply them using convolution along the mode 3, so along this direction k. And we have the tubal SVD. And the Fourier domain is very useful, I would say, or essential for computing this tubal SVD. So what do you do in the Fourier domain? Having this 3-dimensional tensor, you apply the FFT for this tensor along the third mode, which means that every tube that you have in this k direction, every vector that is going in this direction will be FFT transformed. And if you do this for every single element in this tubal tensor, then you will get T hat, and T hat is the counterpart of tubal tensor in the Fourier domain. And then what you do after this, you consider frontal slices of this Fourier domain tensor. So you Fourier transform along dimension k, but then you slice frontally. So you do here frontal slices. And these frontal slices, they give you m times n matrices. And what you do with these matrices, you simply compute the canonical SVD for a matrix. And for these frontal slices, you will have a set of frontal slices, and then you will have a set of SVDs for these frontal slices. And then you can see, okay, I have here U matrices, I have sigma matrices in my SVD, and I have V matrices in my SVD. Then you collect all U matrices and you get a tensor in the Fourier domain. You collect all sigma matrices in the Fourier domain, you will get a counterpart of sigma in the Fourier domain. So it will be also frontal slice diagonal, and you do the same with V. So you have K matrices, you glue them together and you will get a n times m times k tensor. And then having these three tensors in the Fourier domain to compute the elements of the TSVD, what you do the inverse FFT, also along the third mode. And this is how the tubal SVD works. So you have your original tensor in the tubal tensor domain. To compute the TSVD, you need to go to the Fourier domain. You Fourier transform along every mode. You have frontal slices, you do the usual SVD, and then you transform back. Yeah, so this will be also important for us because at some point we will have some elements that are in the tensor domain and some elements that are in the Fourier domain. So in the Fourier domain, all the elements, they will have a bar on the top of it, right? So if you see a bar, then it means that it is a counterpart of the tensor that we consider in the Fourier domain. Yeah, I think that now we should all be on the same page in the relation to the tensor, tubal tensor setting. We recalled all the necessary components, and now we can consider the problem that we were considering during our research. And for us, we consider symmetric tensors of low rank, but I told you that we will have tensor factorizations. And this is why this ground truth tensor T will be a factorization of two tensors. So we have a tensor X, which is ground truth, and we multiply it with itself. This tensor X is of low rank, for example, as is depicted here on the picture. And then because of this, the tensor T will be also of rank R because of the product. It is I mean, I hope it's clear, right? So we have two low-rank tensor, like one low-rank tensor, you multiply it with itself transposed in the tubal sense, and then you will get another low-rank tensor, but it will be a symmetric low-rank tensor. What we assume about the linear measure, about the data that we assume that we have linear measurements of this tensor factorization. So you can think about this as, yeah, I would say you can think about having a very big tensor, making it a very long row vector, and then compute a dot product between them. That's how it works approximately. And we also assume that the measurement tensors that we have, they are symmetric. So we have a low-rank tensor as ground truth, and we have linear measurements of this low-rank tensor. What we also assume about the measurement operator, that it has the so-called RIP property, or RIP stands for restricted isometry property. And we say that this operator has the restricted isometry property of rank R and constant delta if it approximately preserves the norm of every tensor it maps to R of every low-rank tensor. So for every low-rank tensors, low-rank tubal tensors, this inequality will hold. And then it means that the measurement operator has this RIP property. So you see, you have just I would say a data neighborhood where your norm is. So you're not far away from the true norm of the tensor. And the aim is then to recover this symmetric tensor from linear measurements Y. And the ansatz that we use is gradient descent with over-parameterized factorization. What it means is the following. So we take a rank capital R that is larger than the true rank of X. So the X here has rank small r, and capital R is the over-parameterization that we take. Then we are looking for a tensor U that is of this dimension. So it has the second dimension capital R not the small r. And we want to find such u that it approximately represents x times x. So this extra dimension that you have here will go away because you multiply them. So you'll have the same dimension, the same symmetric tensor. If you multiply the same dimension of symmetric tensors, if you multiply both of them here, and we want to find this u in such a way that it minimizes the L2 norm of the measurements. This is the classical approach, right? And for this, we use gradient descent. And what is very important here, that we start with a small random initialization. So the U0 that we have here has the same dimension as we are looking for. So it has capital R, so it is over-parameterized, but it is small, so which means here the variance is alpha. Alpha should be small. And it is random. So in this case, this is Gaussian. And what is interesting about this, such kind of initialization makes the starting point a full rank tensor, right? So if we think about spectral initialization, right, you start with something that has the rank that is equal to the rank of your ground truth. In this case, it's not the case. We start with a rank that is bigger than R. And for us, since we have here the randomness and Gaussian, this will be a small tensor. So it means that every entry will be small, but it will have a full rank. And with this starting point, we iterate we do the iteration steps with the gradient. So this will be the gradient, and these are the gradient iterates for this setting. So as you can see, we can factorize it as follows. So we have here the identity of like the unit tensor, and here is some suitable initialization mu, and then you have a star a, so the adjoint operator of the measurement operator, and here are your gradient descent iterates and the ground truth. And what we want to do here, we want to look at the convergence process of UT transpose. We want to see whether it converges to the global minimizer, and we want to know the behavior of gradient trajectory. So, which means we want to know how it develops, not only answer the question, does it converge to the global minimizer or not? But we also want to see how the trajectories behave, right? So just to sum up the setup, we apply gradient descent with overparameterization to recover x star x times x transpose in tubal sense. And we also have small random initialization. As you can see here, in this case, we have no regularization towards low rankness, right? The initial point that we have is full rank, not low rank. And in the gradient, we have nothing that imposes low rankness. So it means that our algorithm has nothing that should impose this low rankness. And here is the main result that we have. So we say, okay, we have the measurement operator A, and the ground truth tensor has rank R. Then we have measurement operator that enjoys RIP of the rank 2R plus 1 delta. So it's twice the rank of R of X and twice the rank of X. And this constant delta, which means it tells you how big the neighborhood is in which your measurement land in the neighborhood of the true norm. It has this dependence on the true rank and on the condition number of the tensor X. So there is a natural definition of this conditional number. I haven't introduced it yet, but you can think about this as I would say similar as in the matrix definition, in the matrix case definition. And here with this setup, we over-parameterize with R that is 3 times as big as the true rank of our tensor X, right? So at this, I would say some kind of over-parameterization that is not very small. And we want to fit X times X transpose with UT times UT transpose by a gradient iterates, the one that you already saw, right? So we have the a unit tensor and the operators here with a joint operator with some step size that is dependent again on the condition number and on the spectral norm of our tensor. And we initialize, as mentioned before, small n random. And what we know then in this case, if the initialization scale is small enough, then after a particular number of iterations, right, we have that the test error became small. And the upper bound for this test error depends on the initialization scale. And of course, it depends on other conditions that are related to the ground truth tensor. And this inequality holds with high probability. And this probability improves when you overparameterize, which means the more you overparameterize, the better is the probability that this inequality holds. Which means here the overparameterization is an advantage because we know that the probability is high that we will have a small test error, right? Alpha is small, and making the alpha small, you will make the test error small. So this bound for the test error does not depend directly on R, right? Because if you have R that is bigger than N, then you will get here just N. You will get N. So this bound will not be dependent on R, but it will depend on alpha, and which means the initialization is responsible for the behavior of the test error and how likely it is that this inequality will hold depends on the overparameterization. So which means you will have an advantage if you do both, right? You will initialize very small and you will have a big overparameterization. And as I mentioned before, this gradient descent and the train function that we minimize, they do not impose any low rankness. So because of this, from this result, we can say that gradient descent is implicitly regularized towards low tubal rank solutions, right? Because the test error will be small. Maybe if you have some questions regarding this, you can interrupt me at any point and I will be happy to answer them. If I'm going too fast, you can also tell me about this. But
yeah,
if
feel free to put questions in the chat as well, and I'll let you know if and when they appear, Anna. Sorry
yes, great.
for interrupting.
Then let's do like this. Yes,
Hello?
then I think, yeah.
So yeah, I want to ask a question. So, can you explain the intuition that this gradient descent do such a regularization?
The intuition, yeah. So I think this is the mystery of gradient descent, right? So I think this is something that you would not expect to happen if somebody just tells you run a vanilla gradient descent to find a low rank tensor. And it's very unlikely that you will have a low rank tensor when you start with a full rank tensor, but this is something that explains the behavior of gradient descent. So, which means we have no regularization, but the gradient descent is biased towards low rankness. So this, I think this is the intuition. So there is something in the gradient descent algorithm that makes it to be biased towards low rank. And for example, I think that the one useful thing is that you need to choose the right factorization, right? So maybe if you will have here another type of factorization, you will have another implicit bias towards another type of solution.
Yeah, go for it.
And I also want to ask, so here in your result, this big inequality, it is not, so it is not saying that ut is close to x, right? Instead, it is saying that the multiplication result is close. But does this really means low rank of ut?
Yeah, it means, I will show you in the proof. So it means that you will have, at the end of the day, the gradient descent will make your ut low rank.
Wahid, I think your hand was up. Do you have a question still?
My question was the same one that was just asked, which was like, I couldn't see in the theorem statement that actually you are getting a low rank solution, but I presume that's hidden in the proof. So
Yeah,
I
yes,
got
it
the
will
answer.
be in the
Thank
proof.
you.
So it will be not exactly low rank. So it will be approximately low rank. So you will have still, maybe I would like to add something. In your UT hat, there will be no exact low rankness, but there will be it will be approximately low rank, which means if you will have the decomposition of the U in two parts, with if you compare your singular cubes, then you will have a very large part that is dominant and is of rank exactly small r, and you will have another part that is that has the spectral norm much smaller. It is there, but it's not that big, so which means you can somehow ignore it. So it not UT will not be exactly low rank, but it will be approximately low rank. But I think that now I can go to the proof, and maybe it will be more.
Quick follow-up. So for that kind of residual piece that you are referring to having some spectral norm, does the spectral norm decay to zero as capital R increases, or how does that behave as a function of the over-parameterization?
So cannot say that it goes to zero, because we have here some, I would say, upper bound for the iterations, right? So we do not tell you what happens when the t goes to infinity. It is, it is a very good question. Thank you for this. So we know what happens if you go that far. And what we also observe numerically, that it goes to zero. But what our result tells you, if you iterate long enough, right, then you will have a small test error. But we cannot tell you what happens when t goes to infinity. But you will have, in practice, you will never have this. So this is not an asymptotic result.
Hello. So I have a further question on this issue. So this so when you write t hat is less than equal to this many iterations, this less than equal to this symbol is with respect to n tends to infinity or not?
No, this symbol means that you have some absolute constants. So they are independent of the rank of the true tensor. They are independent of initialization. They are just some absolute constants.
Okay, and okay, I see.
Mm-hmm.
And but so you have just mentioned that we are not sure whether this optimization will converge, right? Is it going to converge or not?
I mean, you can make this inequality as small as you want when you do alpha very small. So in this case, you can reach the error that you want, right? And if you run it, it will converge. But our result will not tell you about this. It tells you that if you iterate long enough, then there will be an iteration point where this error will be small.
Okay, but and after that, it is also below this bound, right? So after t
Yeah.
hat, okay, okay, thank you.
Good. Any other questions? Good. Then I can continue. And here I will go a bit more into the proof details, saying you what are the main directions that we go into. So to prove this result, we extend the approach that was proposed by Dominik Stüger and Zoltanol Kolbati in 2021. And they proposed this for matrices. To prove our result, we need to extend this to tensors. And we use this, I would say this is more or less the classical ansatz that for this result, we consider a tensor Vx times u. And so u are the gradient iterates. Vx is the tensor column subspace of the ground truth. And for this matrix, for this tensor, we consider this tensor SVD, tensor tubal SVD. This tensor tubal SVD will give us this tensor WT. And WT and its orthogonal counterpart, they will help us to decompose the elements of the gradient descent into a way that we can analyze them in a rigorous way. And this decomposition is called signal and noise decomposition, which means that the UT will be decomposed into the signal part. So the signal part is this one, and we have the noise part. The noise part is then related to the orthogonal space, to WT. And the advantage of this is that this noise part is, or the column tensor subspace of this noise part is orthogonal to the tensor column subspace of the ground truth of X. And this allows us to have a rigorous analysis of these two parts. So the idea is that the first part, the signal term, will converge to X, and the noise term will disappear when we iterate longer and longer, right? So, which means the noise term will be there, but it will be at some point made small, right? And to do so, we have the following. Our analysis includes two distinct stages of gradient descent. The first stage is the spectral stage, and in this stage, as before, we use gradient descent with small random initialization u0. And what we show in this stage that the first iterations of gradient descent behave similar to a tensor powers method for spectral initialization. So or something that is related to spectral initialization. You need to still take the SVD of this and reduce to rank R, but this matrix is the one that this tensor is the one that is used for spectral initialization in the matrix case too. So you will use this type of matrix or tensor, depending on whether you are in tensor or in matrix setting, to have the spectral initialization. Okay. So this is the reason why it's called spectral stage, because we show that the gradient descent behaves similar to the tensor power method. It means at some point it will the tensor column subspace of the power method and this matrix, they will be aligned, and the same will be about the gradient descent. And in the convergence stage, we show that UT transpose converges to the low tubal rank target, so to X transpose. And we show that this convergence is geometric until we use a certain level on alpha, a certain level of error that depends on alpha. And this certain level is the upper bound that you saw. And what was the key fact that we used, for example, in the spectral stage is that the power method for tubal tensors has the splitting property. What it means the following, that if you run the power method for tubal tensors of size n times k, so your third dimension is k, then it is equivalent to k independent matrix power methods. So if you remember this picture that I showed you about the Fourier domain, where you do the tubal tensor SVD, at some point you come to the standard matrix SVD when you look at the slices, and this is where it comes from. So due to this, we have here a I would say strong relation between the power method in tensor domain and the usual power method for matrices. But there are also key challenges that we need to face when we, I would say, translate from matrix setting to the tensor setting or transfer. The first point is that in the matrix case, if you think about the the range and the kernel of a matrix, they never overlap. This is something that in the tensor setting for the tubal tensors is not like this, or not always like this. There are some tensors for each the kernel and the range overlap, and this can happen when you have something that is called tensor with non-invertible tubes. And in this case, the range and the kernel will share the generators, so they will have common elements in this, which is very bad, because in this case we cannot do the signal to noise decomposition, because we really need to have that the noise part is orthogonal to the column tensor subspace of the ground truth. So this means that we had to exclude tensors that have this non-invertible tubes. What it means that a tensor has a non-invertible tube, it means that, for example, if you look at the SVD, then in the Fourier domain, if you look at this frontal slice diagonal tensor, you may have some tube here that is blue, which means it is not zero vector, but it can have some zero elements. And this would mean that some of the matrices are not in the Fourier domain are not invertible, and this is the reason why you cannot do the decomposition, because because of this some overlapping parts. And another very important point is that if you think about gradient descent, then it mixes Fourier slices, which means that every slice in the Fourier domain of your gradient iterate will carry the full information about ground truth tensor. So, and it is very different from the splitting property of the power method, right? So, which means for the power method, the world is very nice. You just have simply k independent power methods and you run it whenever you want. But for the tensor, for the tensor setting and the gradient descent, it's not anymore the truth. So in every slice, you will have the information about X transpose, which means that the slices are not anymore independent. And here I would like to show you a bit more details on this. For example, for the power method, I would say it's a part that is a bit more easier. We have the gradient descent iterates with small initialization, and these are iterations that correspond to the gradient to the power method, modular normalizations for the tensors. And what we show that for the first few iterations, ut is almost as ut tilde. And here is a bit more exact bound. For some first few iterations, we know that the spectral norm of the difference is bounded by something that is dependent on the initialization. And this L that you see here, it is this matrix. So this is A star A X X transpose. And you see if T is very large, this bound is just meaningless. But because alpha is small, at the beginning, you can see the similarities between the gradient descent iterates and the power method iterates in the tensor case. And what we show further in this spectral stage is the following. We compare subspaces. And here I have several subspaces. So I have here the spectral initialization subspace. This means this is subspace spanned by A star, X star, the first R tubes, gradient descent subspace. This is LT and the signal term subspace. And what we showed that the spectral initialization subspace and the gradient descent subspace are close to each other. And because of RIP, we can also show that that the gradient descent and the ground truth are also subspaces are close. Then after another part of iterations, we can show that the X, the subspace of X and the signal term subspace are aligned, and that we have some gap between singular tubes in the Fourier domain. So singular tubes here is, I would say, a bit more general, because here I show you each element of the singular tube. So we have its element-wise. Mark, how much time do I have?
I would say 10 to 15 minutes.
10 to 15 minutes. Okay.
Yep.
Good. Then I will go here shortly about the convergence stage. And in this convergence stage, what we show that for after this spectral stage, you will have another part where you have here you can estimate the minimal value, singular value of this tensor, and you can show that it grows geometrically. And for the noise term, you can show that it grows slower. So this is, I will not go here a lot in the details, but the main message here is that you will have here something that is related to the signal part, and it grows faster than the spectral norm of the noise part. And after this, we refine the bounds a bit. So we show that this signal term stays big. So the minimal singular value of the signal term is bounded from below. And what we show that this noise term is growing very small, very small. And then we have this, after this, we can show this general bound. So we have here geometric convergence of UT transpose to XXT. And then choosing here wisely T, you can show that you have some dependence then here on some parameter gamma, but then this will gamma depend on alpha, and you will get the bound that I showed you before. I would like to show you shortly numerics. So how do we measure numerical performance? In addition to comparing the full tensors, like looking at the test error, we also compare R singular tubes, and we compare leading column subspaces. Which means here, if you look at this picture, if I have the ground truth tensor X of rank R, I will take the R's tube from here, and I will also take the R's tube from the UT tensor, and I will compare them. This is what I mean by comparing singular tubes. I will compare the relative L2 error because they are vectors, and I will also compare some subspaces. I mean the principal angle between subspaces. So I have the ground truth subspace, so this is the subspace of X, the spectral initialization subspace, the one that you saw already, gradient descent subspace, also the one that you saw, and the power method subspace. So here we have the this L tilde, which means I have here several subspaces that I compare, and I will also compare the test error, the train error, and the singular tubes. And here is one part of the numeric. So here you can see that I have here different curves. So the blue one, it is the principal angle between the spectral initialization subspace and the gradient descent subspace. The red one is the test error. This yellow one is then this relative L2 norm for singular tubes, and then this magenta is training error. So if you can see, when gradient descent iterates, then the errors goes down, and also the relative L2 norm between singular tubes is also going down. And what is very interesting here is the behavior between the principal of the principal angles between these two subspaces. So if you can see at the beginning, the principal angle goes down, down, down. So it goes it becomes very small. So which means that gradient descent as the principal, the tensor column subspace of gradient descent becomes very close to the tensor column subspace of the spectral initialization. But then the principal angle goes up, and the explanation for this is the following. The spectral initialization has a lot of information about the ground truth, but it does not have the full information. That's why to learn X transpose X and its principal tensor column subspace, which means the principal angles that you take a look at, you need this curve to go up, because otherwise you will not learn more about X than that you have from your spectral initialization. And this is something that you can see on this figure here. This is the same blue line that you see here. And the red line is then the principal angle between the ground truth and the LT. So you can see that it goes down at the end. And this is the principal angle between power method, the yellow line, and the spectral initialization. And you can see that the power method, of course, learns the subspace, so it goes to 0. And here is some impact of alpha on the test error. So I told you that when alpha is small, the smaller the alpha is, the better is the behavior of your error. And this is something that you can see on this figure. So the smaller we initialize, the better test error we get at the end. Yeah. And this is log-log plot. So then I think the last slide that I want to show is about numerics is this one. So this tells you how this overparameterization acts on the test error, train error, and principal subspaces. But what you can see here on this enlarged part, that if you overparameterize more, then the test error becomes even better. But it's something that we observe in the theory. We only know that the probability gets higher, right? So this is what we know about the theory. So maybe in some future research, one can also show that it's a bit better. Also, the bound is dependent in some cases on R, but when R goes very big, then you cannot see here big difference. They are also jumping up and down. So maybe it's also not will not improve the bound at all at the end if you over-parameterize very much. Yeah, and here is some conclusion. So in this talk, what we saw that tensors of low rank can be recovered via gradient descent without explicit regularization, and how it helps us to make the first steps towards understanding implicit regularization in nonlinear models for tensors. And also, gradient descent is a simple approach that recovers low-rank tensors without explicit regularization. I think this is I would say the main message of this talk, that low-rank tensors can be recovered for gradient descent without explicit regularization. And what are the follow-up questions? So we are interested in improving complexity bounds. So we, as I told you, we have this assumption on the measurement operator that it needs to have RIP, and RIP gives you, yeah, I would say, the rule for the sampling complexity. We would like to have it better. Another point is that we want to understand implicit regularization for this non-invertible tubes, the one that do not allow for this signal noise decomposition. Numerically, we see that everything also works, but we still need to think about more theory in this case. And what we also are interested about is thinking about other tensor decompositions, for example, the Taka decomposition that you can see here in the picture, or the CP decomposition, and do this small random initialization or parameterization and this kind of factorizations. Yeah. And at this point, I would like to thank you very much for your attention and for coming here, and I'm open to your questions.
Yeah, thanks a lot for doing a great job. I will stop the recording here.